well, we're just waiting for a few more to join on there. Just the house rules. Again, as with our well, first of all, I should say I'm Ian Greenwood, the moderator for tonight, a consultant with the ADB team across a few of their projects and been involved with the Green Road Initiative and several others. So it's good to be back here again for the next exciting episode. Your microphones are on mute. Our preferred way of trying to keep some sense of order is that use the Q&A button, and we'll certainly try and get through all of the questions throughout the session. If we need to, we will, of course, open up your microphones for you. Just to let you know what's coming up, we've got the next couple of sessions in 2 weeks' time. It's doing the infrastructure assessments and the blue dot rating for essentially how green is your project. So with the Green Roads Toolkit, we've of course got lots of methods and suggestions of how to make your project better. This is a formal assessment method that goes alongside that, one of a number of rating systems out there by the blue dot. 2 weeks after that, we've actually got another session looking at the role of network redundancy, and in particular your second and tertiary road networks, in creating a resilient transport system. So please stay with us and keep on joining the webinars. And by all means, share them with your colleagues, friends, family, whatever you wish to do. But for now, I'd like to move into the topic we're all here for, which is the rapid traffic modelling with AI and big data methods. Now, it has been my privilege to have worked alongside Professor Travis for the last year or so, as he's been providing some inputs on an ADB project that I'm involved with. His enthusiasm and can-do attitude when it comes to the area of traffic modelling never fails to come through, and I'm sure we're in for an engaging next hour. Some of you may not have read his bio on the webinar announcement. Travis is currently the Lighthouse Professor and Chair of Transport Modelling and Simulation at the Technical University in Dresden, Germany. Prior to that, he was a professor at the University of New South Wales in Sydney. He was also the head of the School of Civil Engineering, Civil and Environmental Engineering, as well as a Deputy Dean of Research for the Faculty of Engineering. I think those are pretty much all the roles available to one person to hold at once. Prior to that, he had stints at the Australian National University and the University of Texas at Austin. And in both those, he served as a founding director for research. He's authored over 200 scientific papers over his 25 plus years, which by my rough maths, that's around a technical paper per month, which is quite an achievement in its own right. And you add to that all the numerous accolades that have been bestowed on over the past several decades. And I won't try and go through all of those because we'll run out of time for Travis to actually talk. So Travis, it's a pleasure to be able to moderate for you, and the virtual floor is all yours.
Thank you very much for that, my friend. It was a very, very kind and appreciated intro. Let me get my slides up here. Hopefully those are through okay. I believe so.
Yes, yep, that's fine. Thank you.
Awesome, thank you. So, I'll try to move quickly. Well, I've done some startup and other activity. I am still an academic at heart, so I have too many slides. So I will move very quickly, and I will try to skip things that may not be as critical. But as Ian very kindly mentioned, we're talking about rapid traffic modeling, primarily leveraging emerging techniques. I do just want to take a very quick moment to acknowledge that what I'm presenting is the outcome of decades of activity, and there have been massive research groups in place for this. Back through my time at University of Texas, Austin, and I'm very proud of the research team that I had there. And then after my relocation to Sydney, and now here in Germany, of course, in spanning quite a lot of activity over that time frame. And I want to acknowledge, so as not to upset certain partners, that over the years, some of those methods moved out into commercialization, specifically mobility thinking, which is based in Australia and was founded in 2018. And that's the primary service provider if the particular project is more commercial than research in nature. In terms of my activity, really, there are two key pillars. And in my move to Germany, really sort of reconsolidated on these two. One is emerging technology, and that's spanning automation, applied AI, even blockchain research. And we're looking at that for mobility as a resource. But then in particular, evolving social consciousness. And I'll talk about that quite a bit more. And that I think is the real touch point for green roads, but also more broadly, equity, environmental justice, and so on. And sometimes it can seem quite, fundamental research in nature, but there have been a stream of very applied projects over the years. We've done about 40 in the last 25 years or so that have had very practical, impactful outcomes. So Ian already covered the background, so I won't dwell much on this. But in my move to Germany, I took a quick look back, and I want to take just 2-3 quick moments to sort of describe how we've come to where we are. And in my move from Austin, Texas to Sydney, Australia, in that first year, 2011, I went around giving a lot of these sort of talks. And I was curious what I was talking about back then. So the next just 3-4 slides are taken exactly from the slide decks of the talks I was giving back in 2011. And we can see how those feed into what we are doing now. So back in 2011, the first thing that I was always talking about was actually electric vehicles. Back in Austin, Texas, I led a team that established a U.S. National Science Foundation Industry University Cooperative Research Center on electric vehicles. And we started that effort in about 2006 or so. My key partner was Professor Milan Gazunovic, who was a chair of energy systems. And we got that center up, and that was looking at some of these issues, such as the impact on infrastructure, how that relates to how they're funded, the difference in EVs, both in terms of emissions, but also the impact on asset management. And so that was the first thing I was often talking about, and it's fed into the previous 10 to 15 years of research. The second one I was always talking about was environmental justice across protected groups. And to my knowledge, we did one of the very first quantifications of environmental justice for what was the largest metropolitan planning organization in America, NCT-COG, North Central Texas Council of Governments. And we created new metrics to quantify environmental justice specifically for the application of ranking infrastructure projects, so helping to inform how billions of dollars of infrastructure money was spent. And this was quite novel at the time, and that was published and that was recognized with a research award, I believe, because of sort of being a bit ahead of the curve in thinking on this stuff. And that research has continued. How can we include these social values, quantify them into our transport planning in a better way? So that was the second one. The third one I was always talking about was the study of disease spreading and transport networks. And that work was primarily done by my former PhD student and colleague for many years, Professor Lauren Gardner, who's now at Johns Hopkins and probably known to many as the creator of the COVID dashboard. And so that was another key touch point. And then the fourth one was automated and autonomous vehicles. And that work was done jointly with computer science professor Peter Stone. And we did that work starting back in about 2006, 2007. And so those were the four things I was really focused on. And I would like to think there are two key themes, as I mentioned just a moment ago, that emerging technology, how that changes traveler behavior, and how that changes the tools we use to plan transport networks, and that evolving social consciousness, environmental justice, equity, fairness, and so on. And that's really the theme of my interest and how these interact. And then adding into this mix, my original research, which has continued over the past several decades on network equilibrium and how we can create network models that are both more realistic but more useful. And that's really what I want to dwell on now. And so the key driving motivation is that we need planning models. And I think this audience knows that probably as well or better than I suspect. And these models have to have the capability to evaluate hypothetical scenarios. If we change the system or policies around the system, then you will get a new equilibrium point. Your demand and your supply curves will have a new equilibrium, and we have to be able to capture that. And this has been the essence of transport planning for many decades. You know, the classical ways, 1950s four-step process, that is a very standardized process. It's even in Wikipedia. You can go and you can look up the four steps. They're very well defined. For us and for the research I'll talk about today, it's really centered on that fourth step of network route assignment. That's really the driving force of having this hypothetical modeling capability. We want to be able to do that very rapidly and to do that at a very large scale. That is our objective. Now, that process is really driven. There's a very famous formulation, Beckmann's formulation from 1956. It's a convex mathematical program. To some, it may seem very simple. To others, it may seem esoteric. But I would argue it's incredibly practical. It's the driving force in most of the software packages we use for transport planning, that this is embedded within it. And within that, to solve that formulation, often that's some sort of optimization, and very often that optimization is driven by shortest path algorithms. That's often the entry point to solving the network-wide assignment. And the output, you get the link flow on every link in your network, and the input being the origin destination trip values. And in the historic four-step process, those are derived from a statistical procedure, often beginning with household surveys. And that's really the point of innovation. How can we do that in a much more rapid way, leveraging emerging AI and techniques and big data? But keeping that behavior is absolutely critical. And in essence, that formulation is capturing a very simplistic Nash equilibrium, sort of a game theory, but it is powerful in its ability to evaluate these hypothetical scenarios. Now, over the past 60 years since the Beckmann formulation, there's countless research that has been conducted, making these more complex, thinking of stochasticity, thinking of dynamics, and these are very valuable contributions, and some are tailored for certain applications. You really have to dive into those. For other applications, if they're at the aggregate level, the standard practice worldwide is still that very traditional Beckmann-style approach. And so our starting point is, how can we make that virtually automated? As a very quick aside, just sort of to demonstrate that, I won't dwell much on this from time, but these really are at the center of much of the fundamental mathematical side of my research over the past 25 years, all the way back to my PhD for stochastic shortest path algorithms and how that shows up in adaptive equilibrium approaches. This is just one example showing the difference between a deterministic shortest path and an adaptive stochastic shortest path. I often like to go into this, but again, for time, I won't dwell, except to say that this is a novel routing approach that requires a new algorithm. That research has been delivered a long time back. It's now virtually standardized. So there's a new approach for shortest path. From that new algorithm, you can derive a new version of Beckmann's. So this is effectively an updated version of Beckmann's that includes that stochasticity and adaptivity that was published in 2009. And that would show a new type of adaptive equilibrium, a novel equilibrium versus the Beckmann style. And you can show some interesting results. You can do, for those that are familiar with Bray's paradox, you can show an equivalent of Bray's paradox for information. The model's capable of predicting such a thing. And that's been published, and as I said, I won't dwell too much. But the question then was, is that practical? Is that useful? Do people actually behave that way? To look at that, we did some experimental economics. We actually gamified some experiments and had people play this through. That was published in 2017. We had 144 participants basically playing this game of network routing over and over. And what we observed is, over iterations, so they grew in familiarity with the system, you can observe an equilibrium set in, an adaptive equilibrium. And you can actually observe some interesting phenomena. You can construct cases where, for instance, in a no information scenario, your total system cost, your average travel time, could actually be lower than when people have information. And that's one of the power of models, is we need these models to predict complex, potentially non-intuitive behavior. We can't just put the network up on a map and guess at what might be the outcome. We have to represent the behavior within the model. And, at essence, what does it mean showing this sort of result, where counterintuitively we provide information which we would expect to help the system, in some situations could hurt it? And we came up with an observation that was part of the 2009 paper. In the absence of deception, inducement, or pricing, the power of information is that it makes us more efficient at being selfish. And for mobility, that can lead to the classic tragedy of commons outcomes, and it can lead to it even more quickly. And that's really the key, again, power of the modeling, that it can help us to see these sort of situations where we make a change and the model says, the network will respond in a non-intuitive way that might be good or it might be bad. I'm careful not to imply at all that information generally hurts. What I'm saying is it can. In certain situations, it can, in the same way as infrastructure in the Bayes paradox example. So these models are important. They help us to describe what's going on and to evaluate these hypothetical what ifs. But if we accept that network rerouting behavior is critical, how can we actually keep that? How can we embed that in these emerging methods and data? How can we keep that which is most important for transport planning at the same time as taking advantage of this explosion of technology and data? And that's really at the essence of automated modeling and rapid planning, is embedding that equilibrium. So given the importance of network modeling, we want to cut the time to deploy the models. We want to evaluate them, develop them very quickly. And in doing so, we might be able to standardize them across regions, increasing transparency and engagement. And that opens the possibility of incorporating new metrics on equity, sustainability, environmental impact, justice, and resilience, because we're standardizing and automating the process of the model creation. I do want to note that this now current work is done in partnership with NVIDIA. They're a good collaborative partner of ours, and we have an ongoing relationship with them in developing these techniques and more on the visualization. Now, given that, what really is driving these? A couple of things I want to note and acknowledge. Back at my time at UNSW, I think around 2015-16, we were very fortunate. To my knowledge, we were the first group outside of America to get the Google Maps Outreach Grant. So we had effectively had access to all of the Google traffic data worldwide for about a year. And so we started really getting in relatively early, understanding what the data can do, what it can't do, how to access it, how to package it, and then how to use it to inform the models we develop. And so that's really where that work started to take hold. And then we also looked more broadly at the landscape, and some of these players have sort of fallen off over the years, but that's back from a 2017 paper where we looked at different types of emerging data sets and how they can be used for travel behavior modeling. And so that work's been going now for almost a decade. And then the end result of much of this is this rapid planning methodology, where we'll begin building a supply model. So a network supply model out of OpenStreetMaps, which many people are doing, but sort of overlaying that with an understanding of roadway capacity. So using things like the U.S. Highway Capacity Manual and other information sources on how to translate parameters of the system into a meaningful capacity within that's relevant within the context of planning. So link cost functions, BPR type capacities. But then using AI techniques, in specific for this application, evolutionary algorithms. But the real innovation is embedding that network equilibrium within the machine learning. And that is still quite innovative, I would assert. And I'll talk more about that in a moment. But effectively, every fitness function, so this particular machine learning approach has a fitness function within the genetic algorithm that proceeds generation to generation. And every single fitness function is embedding a network equilibrium. So we're solving tens and tens of thousands of network assignments, equilibria, and using that to evaluate the fitness of a particular trip table in terms of how well the eventual outputs will match to the observed big data. Other sort of inputs include things like the Google point of interest, WorldPop demographic data, and others, particularly in creating the initial solutions to the genetic algorithm. And that's very important for computational efficiency. There's just a few papers talking about this specific now overall approach. The overall framework we published in 2021, this is how it looks. In that top section, that's really the supply model. So starting with OpenStreetMaps and then other rule sets that we've derived, coming up with a supply model that includes, for every link in the network, a BPR-like function that has a capacity and the free flow speed, but then will provide the cost of the link as the flow varies. That's really that top branch of the framework. The bottom are the initial demand solutions. So the key variable here are the origin destination trip values. What is the OD? And that's what we want to find. And we want to find an OD such that when that demand, the origin destination demand, is equilibrated on that specific supply model, and that's the network equilibrium box in the middle, which is really the heart of it and the key innovation. When that demand is equilibrated on that supply, it will produce modeled metrics, the forecasted flows, travel times, and so on. And what we do is we compare those to the observed. So from Google and elsewhere, we have the observed travel times. And then in particular, if we have a relationship with local agencies, we often, especially for the ADB projects, will have official AADT counts, and we want to match those. We want to find an OD that, when equilibrated, matches these values. And then the evolutionary algorithm, the genetic algorithm, is the glue between these that will iterate through tens and tens of thousands of these to find the OD that, when equilibrated, best matches the observation. And that's really the driving force. And I would argue this is, for our profession, the ideal way of combining the emerging machine learning techniques, big data that's now available, but keeping the essence of what's important for transport planning. We have to maintain that demand-supply equilibration. We cannot let that go away. Otherwise, what we end up with are analytics. We do not end up with a model. So the output of this is the supply representation, the demand, and combined, they create a network equilibrium model. You can make changes in the network or the demand, re-equilibrate, and evaluate hypothetical what-ifs. And that's what we really need from the model, being able to evaluate these hypothetical what-ifs. And that's the output of this process. These are just, for reference, some of the papers over the last 25 years or so. Fortunately, we started pretty early looking at evolutionary algorithms, machine learning for transportation, quite before I think they were even in vogue. So we have some good experience on how to deploy these specifically for transportation modeling. These are just some details on the genetic algorithm approach. The way to think about it, there is a chromosome. The chromosome represents the origin destination variable. And there are many, many of these chromosomes, and they form a generation. And generation to generation, they are refined by the genetic algorithm, the evolutionary algorithm. And there are many options in terms of initial solutions, fitness functions, and that's what much of the academic research is on, in terms of determining what is the right fitness function, what's the right family of initial solutions, so that you can get a computationally efficient approach. And so that's really where the academic research comes in, is refining this machine learning optimization process. And we would argue this is a very good example of sort of academic to practical research transition. The very first case study we looked at was looking at Sydney, because that was home at the time, and we had access to the Sydney strategic model and even access to the household travel survey. And we looked, and at the aggregate level, things lined up quite well. And I could refer to the paper in terms of more details on that one, but that was sort of the first case study. This is how the Sydney model looked in terms of the zonal structure that was determined at that time, and then the resulting volumes and various metrics on link flow. The second application we did was in Hyderabad, India, and that was specifically to evaluate the construction of a new metro, where we established one of these rapid planning models, quite quickly. I think that whole project was several weeks or a couple of months in length. And that was the second. The third real case study we looked at was Ukraine, because we realized that given the nature of this way of creating a traffic model, we could evaluate certain types of problems which historically were just not practical to look at, even though they were very important. And so we've published a couple of papers now on modeling we did during the war in the Ukraine, starting, I think, on the third or fourth day, and then modeling 8 cities throughout the Ukraine, especially during that first year of conflict. And to our knowledge, these are the very first papers looking at travel network behavior during wartime for those who remain in place. There's been quite a lot of very important, vital work on evacuation, migration, absolutely. But looking at those who are remaining in place and still trying to conduct their lives, to our knowledge, there was no work before these papers. And actually, one of the driving forces on this is a Ukrainian PhD student that's working with me. And as she puts it, her family, her friends, everyone back in Ukraine are still trying to live their lives. They're trying to go to school, go to work. And so they are moving through their networks even while the conflict is going on. And so that's important to model, both in terms of understanding the impact of human conflict on travel behavior, but that can also give us a starting point to trying to think of how to design city networks to be more resilient to human conflict. And so that's one of the long-term research goals of that study. We've also in parallel created a timeline of impactful events that's available off of my chair's webpage. And we've looked at that relationship between specific impactful events and the travel behavior response. And again, that's only becomes possible with these emerging type of techniques. In terms of ADB projects, so the very first ADB project where we deployed one of these rapid traffic models was for Armenia, and the models shown there. And we modeled the route assignment, various metrics on the link flow. We've calibrated that to match that to the official AADT counts and whatever data we could obtain locally, and that's now in some ADB reports, I believe. The second project that we looked at was a broader South Caucasus model. And so that included all of Armenia, all of Azerbaijan, Georgia, and then parts of Iran, Turkey, and Russia. We actually developed 2 models, one very large, over 20,000 networks, quite sizable. But then by request, we streamlined that a bit to only the higher classifications of roadways, which was still almost 7,000 links across the system. For that, we again compared that with official AADT counts, and we did multiple what-if scenarios. The key one being some analysis on potential border modification, and then what that might result in terms of gained efficiencies in rerouting, especially from the base case. And that was delivered and I hope and believe a bit insightful. And then very recently, just within the past week or two, we've been delivering the same, using both the Armenian and the South Caucasus model. We've been feeding into a post-disaster needs assessment that's being conducted right now due to the major flooding in Armenia in May 2024, because the M6 was closed temporarily. And so evaluating that both across Armenia, but then the broader region. And again, that hypothetical what if, that's only possible by having that sort of modeling philosophy in place from the very beginning algorithmic viewpoint. And so that was the second project. The current work that's currently in draft, we've developed a nationwide Tajikistan road network model. And similar story as the others, we did get very kindly by the Tajikistan staff, got us AED counts quite quickly, and they accelerated their work, which is very appreciated to help us develop the OD tables quickly. And that's the network shown there. This one's currently in draft, and this is only one part of a much broader, ambitious project, which is looking at multi-hazard risk analysis, considering environmental disruptions and others. So how can we do this broader economic consideration, but often the starting point is having this type of network model in place, and then it can feed into that economic analysis. And that really, I'll return to that point a couple of times. One way I like to think of this is, I think we are at the point now with the techniques that we have where we can automate the standard stuff, and we really should have a mandate to do so. The basic traffic modeling at this stage should be virtually completely automated. And what that does is, we should be able to do in a few months what historically might have taken 1 to 2 years. And by doing that, it frees up time. It frees up time and resources to look at these emerging critical things like multi-hazard risk analysis, like equity, like environmental impact, environmental justice. We have the ability to do these now because the stock standard stuff can be done so quickly. The initiating work we've just started is on Pakistan. And so we have extracted that network and we've started some calibration on that, but this is literally what's going on these days. And so that work is now underway. So moving past that and a little bit more, I think, to the theme of the workshop, so given that if we can do some of the stock standard stuff automatically and relatively quickly, what does this allow us to do more? And I would argue environmental justice, equity, these emerging social values are what we need to incorporate into our modeling process more. And luckily, we've, as many others have as well, been looking at this in various ways for quite a long time, in particular the environmental justice work I mentioned earlier. This was just a highlight from that earlier work where we came up with 8 different metrics, because that's one important thing when looking at environmental justice or the equity work. There's no one true ethics. There's no one perfect framework. And so there are different ways of measuring it, obviously. And so even in that earlier preliminary work, we had 8 different metrics. Some of them correlate highly, some of them do not. Some of them will lead you to different rankings. And that's an important work to undertake, is what is the best way to quantify and evaluate these. And for us, this was really the starting point of that. The way that we view it now, so in our own work, my last Australia Research Council discovery grant was on ethics-based metrics. And the way we're approaching it is there are different philosophical viewpoints. One is kind of a traditional utilitarian, the greatest good for the greatest number of people. Others are sort of a Rawls egalitarianism. You want to maximize the welfare to the least advantaged user group. Those who are most marginalized should have a much greater consideration. And then there are many variations from there and many things between. Something I have identified, as many others have as well, there's some very good work. This is only one by a researcher out of Delft, Jaffino, who structures it this way, which I found very convenient and useful. Unit, shape, and scope, where unit is the item of consideration. Are we talking about travel costs? Are we talking about accessibility, pollution, safety, so on? That's the unit. Scope would be, what are the points of differentiation across the population? Are we doing it based on income level? Are we doing it based on gender? Are we doing it based on age or physical ability? What differentiates the population segments? And then the trickiest is the shape. What is the philosophical definition of equity, the theory of justice? Is it no one should be worse off from the project? Is it, again, that utilitarian greatest good for the greatest number of people? Is it more of a capabilities? We would ensure a minimum level of service for every group. That has to be defined somewhere. We would argue that's really the role of governance. From the governance structure, the unit, shape, and scope would come. But if you define a unit, shape, and scope, from that point, it becomes an optimization modeling problem. If you tell me the unit, shape, scope, I can devise a metric, I can devise the model, and I could provide the analytics and the planning. But that unit, shape, and scope has to come from some sort of governance procedure. But that's a nice differentiation between the mathematics, between the analytical work and the social sciences work. So this is just one snapshot of some ongoing work where we're looking at access inequality, and in particular, this concept of equity over time. And so that's the citation on the left. It's currently under review, but where we're using a case study in Canberra, Australia, and looking at bus frequency, and looking at that across different segments of population, but in particular, acknowledging that we may not have enough resources to make it fair for any one point in time. It might have to be where certain communities are serviced some of the time and not other times, but over time to have that equity balance. And so that's looking at what can be achieved based on the planning horizon. How many different segments of time do you have available for that balancing to take place? And so that's sort of the concept of equity over time. But again, that matches up to this sort of modeling we're talking about. And then something quite recent is we're looking at how these relate to noise, in particular across protected groupings. And so we're doing that case study here in Dresden. And we're building off some city planning work that they have available here, but then critically coming up with, based on those protected, unprotected population groups, coming up with ways of, from the outputs of a traffic model, flow, speed, and so on, bringing that into noise modeling, and then considering the disparity. So we've developed a disparity index to talk about how that is falling across different population groups, and if more marginalized or disadvantaged groups are suffering more than others, and quantifying that within the modeling. And so that work is also current and ongoing. And then the other key ongoing work is specifically on road vehicle carbon and emissions modeling. And so that we've been conducting scientific work for some time that's now moved more into the practical stage, where we are taking the outputs of these traffic models and putting them into the road carbon modeling. We have 3 different methods that we're looking at. The first is were developed by Professor Matthew Barth, who's professor at University of California, Riverside, who's been working for a very long time on developing these equations that relate to traffic flow into carbon emission. And so we're linking up with his, and we've been doing some calibration comparisons with the International Energy Agency reports on carbon emissions. We've also looking at 2 other methods, including the moves, and then some other methods particularly used here in Europe. So 3 different methods for looking at this carbon emission. And then we've developed a series of city models, global city models. So trying to do some apple-to-apple comparisons on road carbon emissions based on this rapid traffic model that can now be developed. And there's, to my knowledge, a potentially novel observation that we're seeing. So because what we're doing is a model and not just an analytic, we can change the model. We can ask a what if. So for each city, if the demand is taken up or down, what happens to the road carbon? And what we can observe is that the carbon emissions vary nonlinearly. Now that should be intuitive, but what's interesting is the slope of that nonlinearity differs by city. And so you can see these crossover points. And what these crossover points are showing is, if you take just the current situation, you may have 2 cities where one city is emitting more carbon. But if both cities experience the exact same population or demand growth of travel, their ranking swaps, because one city is simply more sensitive to demand fluctuation in terms of their road carbon. And that's important because, to my knowledge, that's not been previously observed. And I would argue that's because we've not had a model like this to look at it. But it also says that in terms of where we need to focus our attention, we might not want to focus our attention just at the biggest carbon emitters. We really should be targeting those who have the highest carbon gradient, because per unit dollar into the future, we should in principle be able to reduce carbon the most. And so this is a new modeling lens on looking at carbon in this way. And you have to have a model in place to do something like this. And so much of our work really is focused on this at the moment. And those papers are in preparation and submission literally right now, these days. And you can see that the rankings would change. So just on these cities as an example, if you look at the emitting intensity on the left and rank them just in terms of their total carbon emissions versus the demand sensitivity, the carbon gradient, that slope. Some of them stay the same. Paris is just high, Dallas is just low in a way. But many of them will change. And so our focus and our attention would change with that. So it's a different sort of metric to be looking at, that carbon gradient, carbon sensitivity, slope of carbon, however we want to define it. The next question that always arises and is always asked is, why are the cities different? Why do some cities have a greater carbon gradient than others? And we're doing a statistical analysis on that right now. Some of it is based on density. Having a more uniform demand is a bit different than having it very dense, but that's definitely not the only one by far. Other things that we've found at some points relate to straightness or security of the network design, how these networks, because all of these networks, because they're global cities, have their own history of how they've come about, and they've been designed in very different ways. And some of them might be more susceptible to this carbon sensitivity than others. And that's a very interesting topic that really we're just beginning to look into. And so understanding that, I think, potentially could have some implications on city planning, city design, because clearly we would want to design cities that are resilient to this sort of sensitivity, because the demand will potentially grow into future. So I think we're doing well on time. So quick summary. So from the fundamental research to date, we now are at a point where we have these methods for the stock standard stuff. We can do them in a very automated, rapid way. And so we can observe some significant efficiencies. And that frees up time and resources to think much more creatively on these emerging problems that increasingly in transport planning we have to be looking at. Environmental impact, green roads, equity, environmental justice, and so on. And that, for me, is one of our ongoing goals, though. The more that we can automate, the better. It's always a situation in every profession. We're always fearful of automation. We always think this is going to reduce the work that we have to do. And I would argue very strongly, absolutely not. In fact, we have a mandate to automate everything we possibly can. Even with that, there is much, much more work to do because of all of these emerging considerations. We need to free up our time to focus on this stuff. So we have to be automating everything we possibly can and standardizing it. And also by doing it in this way, by being able to automate and do things at scale, we can look at problems that historically we could not. The Ukraine example was one, but this carbon sensitivity is another. Really, we can only look at these problems with these sort of automated techniques. Using historical methods, household travel surveys and so on, it's just not really practical to be able to do that. But then I would say most critically, the thing I will repeat until I am hoarse and probably annoy people terribly, in doing all of this, we cannot lose the fundamental ability to plan through hypothetical scenarios. Much of the work in this space, sometimes I'm a bit critical because it tends to drive towards analytics. And if it's purely an analytic and not a model, we cannot evaluate our hypothetical scenarios, which is the essence of planning. If we cannot evaluate how does the flow change, how would the network change in response to our alteration, then in the end, we can't really inform planning at all. And that's my opinion. And with that, I'm happy for any questions.
Thanks, Travis. Fantastic sort of insight there across a whole range of things. So very, very much appreciated. Ross, can I just ask if you can type your question in the Q&A? I see you've got your hand up, but if you put in the Q&A, we'll get to it. And I will go through some of the other questions here in a moment. But first of all, I want to ask you, Travis, a number of countries I work in, and I also happened to work in Ukraine a while back, so it was interesting there, but a number of countries are starting out trying to get a traffic counting strategy in place. They have, so we've been working with them to say you should actually have a logic to why you're counting and where you're counting. And what now becomes more important then? Is it having really good counts in a few spots, or is it coverage with lots of spots? Is it even worthwhile doing OD surveys? Like what advice do we give to people with these new models?
Well, that is an excellent question. I mean, obviously, in an ideal world, we would know all of the flows on every link all of the time. But given the practicality of resource constraints, we're at a point now from various sources, we can get an insight into travel time. So usually we can get a pretty broad sense into that. But what is difficult to obtain often are flow counts. And that really helps anchor the modeling. But you wouldn't necessarily need to have them everywhere to still get, because you have the travel times everywhere. It's most critical to have targeted flow counts on the most critical facilities. That's really the foundational thing. If you can do more is great. but having that as an anchor point for the most critical facilities in your network is very valuable to getting the modeling matched up.
Excellent. We'll go through the questions here then from Dribba. Could you please elaborate on how to conduct a household survey, OD, trip generation, modal choice, route optimization, just a setup of the survey, please? That's a fairly big question.
That's a fairly big question. That's a bit of a standard question. So we teach that stuff in courses. I think that's relatively standard. There's always differences. Some cities do it quite differently than others. It also depends on if you're doing a 4-step process, or if you're doing more of the activity-based. And every city, so I worked with many MPOs throughout America, many DOTs, and then in Australia, every place tends to do it a bit differently. And that starts becoming very localized and bespoke. And that's really the alternative of the approach that I'm talking about here. It's really an alternative to that bespoke process that I'm talking about with these emerging techniques. And I'm not saying that that's not valuable. Having those household surveys is very valuable when you can do them. But there are many places in the world where that's just not an option. Or if you want to look, even when you do that, it tends to be a very one-off process, where these emerging techniques can be run for a specific day. You know, my dream, the sort of mantra I've given for the research side is I eventually, and that's one reason for teaming with NVIDIA, because that's what I shared with them. Eventually, I want to get to a point where we can model every city in the world every day. Because we're getting the travel times every day. If you're also getting flows every day, we can rerun this modeling every single day. And that's really the goal, but it's an alternative approach to that survey.
Very good. Next question there from Ralph. Have you studied different nudges to reach system optimum? For example, sharing info that are not real time to nudge people into rerouting based on desired flow, given road users work selfishly as observed in your previous study.
More on the research side, or in some past work for Texas Department of Transportation, the primary nudge would be congestion pricing. I've been, as many global experts have been, I tend to be critical of giving false information. Like I don't think it's undermining to governments if we were to tell people a route has a different travel time than we know that it does. So I think that's a negative nudge. But nudging them via congestion pricing, there's a vast amount of research, and we've done some as well on congestion pricing to try to move people into more system efficient routes.
So you're saying it would be highly unethical for me to say the route I'm on always comes up congested, so everyone goes elsewhere and I get a free run.
Yeah, exactly. And it undermines trust in the system. And I think now, as we're learning with AI and everything else, we never want to do anything that undermines trust in the system.
Yes. Next question there. What are the main challenges to the implementation or buy-in of these rapid models?
There's always challenges. Relative to the traditional process, the challenges are far less. You can get one of these models up using only travel time, but the ideal is to get some degree of local AADT counts. And so generally getting that data is the primary early activity to getting them up and running, is having a source for some flow counts. Having said that, you can do them based on travel time alone. It really depends on the questions you're asking. If you care about individual route flow, then it can be quite important to get those AADT counts to calibrate. If you're looking just at the aggregate network level, like just a very aggregate network metric, then it could be sufficient to base it only on the travel time. But especially if you so for instance, the border crossing work in South Caucasus, it was very important to have the border crossings, representative of what's going on there. And so it was important to get that data.
The next question from Noriel. Great presentation, which I think was endorsed by no doubt all the different people, but it seems that the work of the new model calibration tools focus mainly on private modes of travel. can you share the implications and potential of these new approaches towards improving and perhaps increasing the share of public transport in cities?
Absolutely. And we have done those as well. Those start becoming a bit more bespoke. We're just starting in January a new project here in Europe, using rapid planning for 15-minute cities. And obviously that's much more about your walking, cycling, and so on. That starts becoming a bit more bespoke because there's not completely standardized, globally ubiquitous data around public transport like there is for the private usage. We can get the travel times virtually everywhere now. So it's really a question of that data source, why that work is more bespoke. So we've created these to be a bit technical. It does increase the computational complexity about tenfold, because what we do is within the fitness function, we still have network equilibrium, but we embed a simplistic econometrics mode choice. So we embed mode choice with network equilibrium within the fitness function. And so we simultaneously estimate an OD table and a modal split. It takes longer to run, but it's still practical. Instead of running in, let's say, a few days, it'll take a few weeks. So it takes longer, but still within reason. But how to get that data and get that into the system, a human has to be in the loop for that.
As an aside, I'm reminded when I was working for a company many moons ago, and we were doing a traffic model for another country, and we sent our traffic counters out around the city, and we drew intersection diagrams and put X's of where the people should be standing to do the traffic counts. Turns out some countries get very nervous when you start putting an X on their Ministry of Defence building. Our traffic surveyors had no idea that they're just looking suspicious, and so
these are the realistic considerations that we planners and modelers often just do not really appreciate at first.
Before I get to Drubba's question about the emissions, how do we deal with different vehicle classes in the model? Like, do we need to be looking at the heavy vehicles? Like, how do we pick up that within it? Can we do it, or do we still need to be doing something else?
That's an excellent question. I could have fed you that, but I didn't. So that, even from doing the Armenia work, that was often a question back. The models that I presented here today are just an average traffic flow without classification. If there's local data on that, we can use that to determine a split. We have what we believe is a machine learning big data way of coming up with a fleet decomposition. We just submitted that paper to the Transportation Research Board. I can share the draft, actually, where we use, in Sydney, quite fortuitously, they have some counters across the city that do the counting with classification included. And we're using that as a test case. And what we've looked at are land use zonal characteristics, including things like Google POI, but other demographic data. And what we're exploring are statistical correlations that could spatially predict fleet decomposition. Once calibrated and then confirmed in at least one or two other cities, what we're planning then is to use that as a big data method for doing the fleet decomposition on any other city that we do rapid modeling of.
Okay, so coming back to my previous question there about traffic counts, so the classified counts still very much a valued commodity.
Yes, although the benefit, if they don't have it, so the goal of that research I just mentioned is, if we don't have that information, we will use land use characteristics, and also something, as many other researchers as well, we've been using satellite nightlight data that you can get in most places around the world. And you can even get metrics, like for a zone, how intense that light is. And something in freight modeling, the satellite nightlight data tends to be correlated with wealth, and wealth tends to be correlated with freight movement. And so from things like Google point of interest, from satellite nightlight data, from other demographic data, we are developing a statistical model that from those data sets could help predict what the fleet decomposition would be. So if you don't have that, we can rely only on that other data. But again, if they have that those classified counts, that would make the resulting model all the better.
Excellent. And that leads us straight into our second question there about how do we predict carbon emissions? Do we do it separately for each vehicle?
If you want to do a dynamic model, so the outcome of this is static. It's traditional transport planning. Much of my actual original research was on dynamic network assignment, but those models tend to be at least 10, if not more times computationally intensive. But if you want to do more of a dynamic simulation, you can start with these to have a demand estimation and a network supply, but then take it into a dynamic model where you model each individual vehicle separately. What we're doing for the current work is we're using the aggregate traffic flow, so the flow on the links and the speed of those, and then from Professor Barth and MOVES and many others, there are equations which will predict a carbon emission even from that aggregate but still link level flow. If you have a fleet decomposition, you can make that carbon emission all the better, but it's still based on that aggregate link level data, which is sort of the traditional static approach, but you can feed it into any sort of micro simulation package as well, Sumo, PTVs, VisSim, and so on.
And I don't think we have any more questions there, but people are welcome to type them in still. Or if someone's sitting here and thinking, hey, I've got a city I'm very interested in or a region I want to study, what is the process to get from where they are to getting an answer like what you're producing? Do they, reach out to you and say, hey, I'm in city XYZ, I want a regional model, and
yeah,
a couple of months later, hey, presto, it's arrived? Is that sort of
That's basically it. Exactly. We tend to be doing that more and more. So we have a scientific research stream, and then there is the commercialized stream by the firm. The scientific research stream are things like the Ukraine and our emerging equity and resilience work. If it's sort of a stock standard, we just need a model to do XYZ, that would be more from the commercial side.
Another question here I see from Ariel, which sort of picks up on that, is can you share the modelling framework and analytical pipelines that can do a similar work for local cities in developing countries? Can you make your modelling system open source, or we would like to collaborate with you?
Yeah. Well, I love to collaborate. I spend my days on Zoom with all of my friends around the world on collaboration, so I'm always looking to grow that. So that's happy to do that. On the research side, we do love doing things in open source, but then there are always some exceptions. So the stock standard stuff is now not within my ownership or control. That bit has been commercialized, but I can help nudge and direct that a bit. But that's now sort of beyond my direct ownership.
So I think the answer there is reach out to Travis and he'll point you in one direction or another. I see we're at full time. I would just like to thank you again for a fascinating insight. I do think back to my days of, having maps out all over the floor of the office, drawing, counting and coding up Saturn traffic models and ME2 models, and I think the sadness that the youth of today won't get to experience such frustrations. But anyway,
well, we'll give them many of new ones.
Exactly. So maybe a new frustration is just as good as an old one. But I'd just like to thank you again. Give you a virtual clap, and we'll catch up, no doubt, in the coming days and weeks ahead. So thank you. Thanks to everyone for your questions, for staying with us, and have a good day.
Thank you all. Really appreciate it.